Hi, hello, welcome to Mickey Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement for creating these kinds of technical videos in the public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of doing these kinds of technical videos in the public domain. And I would like to thank Almighty for my good health and broad mind, and my friends, followers, and my dear students and subscribers for their continuous support and encouragement for creating these kinds of technical videos. Today's topic of interest is iron carbon equilibrium diagram. In this name itself, we can notice that this is the binary phase diagram because we have a iron and carbon. We are going to deal with iron and carbon family, and the iron and carbon in this percentage, which is called as a equilibrium state. That is why it is called as an iron carbon equilibrium diagram. First of all, we have to see the iron carbon equilibrium diagram, this iron carbon family. This is the binary phase diagram which we are going to discuss. In x-axis we are having carbon percentage of a carbon, and y-axis we have a temperature. Here in the iron carbon diagram, the carbon percentage starts at 0 degree 0 percentage to maximum amount of 6.67 percentage. Beyond the 6.67 percentage, the carbon won't mix in the iron. Therefore, the maximum content of carbon in the iron is 6.67 percentage. This we have to know. And here, the left hand side, in the y axis, we have a temperature in degree Fahrenheit, and the right hand side, the temperature in degree Celsius. The maximum melting point of the iron is 1536 degrees Celsius. So, in this temperature, the iron and carbon will in the form of liquid state. Here, the varying percentage of a carbon and varying temperature is the diagram here. The phase changes, the what are the phases? Basically, we have a two structures in the iron carbon diagram. One is phase center cubic and body center cubic. In the if you see here, in the alpha and delta phases, it is in the form of BCC structure, and the gamma phase is in FCC structure. You see, notice that. So this is the alpha phase, and this is the alpha phase, and this is the gamma phase. These two phases are BCC structures, or the form of BCC structures, and here this form is a FCC structure, phase center cubic structure. This is gamma ion, where alpha we have a four different types of ions: alpha, beta, gamma, and delta, where alpha is the ferritic state. We can't notice anywhere the beta ion. Beta is the unstable state. Here you have to notice that alpha, gamma, and delta are available in the state in the iron carbon equilibrium diagram or iron carbon phase diagram, whereas there is an ion called beta ion. Beta ion is always unstable condition. That is why in the iron carbon equilibrium diagram we can't notice the beta ion. So this you have to notice that. Therefore, the remaining alpha ion is a ferrite ion, and gamma ion is an austenitic ion. Austenitic in the form of magnetic, and delta ion is called as a delta ferrite. Delta ferrite. Here the lines like the A2 line, A1 and A2 line, this is the A1 line, this is ACM line. All are very very important one. Here, if you can notice that with this diagram, I can even explain the phases, but for your clarity, I'm going to make it in a theory mode. So here you can notice that the purest ferrite ion is in the order of the percentage of carbon is 0.025 percentage of carbon. This is called as a ferrite ion. Here, if you can notice that up to 0 to 2.1 percentage, this is called as a steel, and about 2.1 to 6.67 it is called as a cast iron. In steel, up to 0.8 percentage, up to 0.8 percentage, so the at the 0.8 percentage it is called as an steel, eutectic steel, eutectic steel. And this is, sorry, eutectoid steel. And this is hypoeutectoid, hypo, and this is hyper. Similarly, up to 2 to 4.3 percentage, at the 4.3 percentage we have a eutectic, and 2.1 to 4.3 it is hypo, and 4.3 to 6.7 it is hyper. The meaning will come in later. Therefore, you have to notice that at the 0.8 percentage of carbon, it is called as a high eutectoid steel, and eutectoid have a 0.25 to zero point 0.8 we have a hypoeutectoid, and 0.81 to 2.1 it is a hypereutectoid. These three are in the steel phases, and at the point 4.3 percentage of carbon it is called as a eutectic cast iron, and 2.1 to 4.3 it is hypoeutectic, and 4.3 to 6.7 it is hypereutectic. So this you have to notice that the maximum solubility of the carbon in the iron is 6.67 percentage, and after that it won't soluble in the iron. So at this point, at this juncture, 0.025 percentage of carbon plus iron, it is in the purest ferrite state, and the iron plus 1.7 percentage, the 1.7 percentage here, it is called as a austenitic steel, and iron plus 4.3 percentage of carbon, here it is called as a leduborate, and iron at the 0.8 percentage of the carbon it is called as a pearlite. So pearlite is in the form of ferrite and cementite. Pearlite is in the form of ferrite and cementite, the maximum percentage of a ferrite and the least percentage of the cementite, which is called as a pearlite. And at the 1.1 percentage of carbon and iron, it will form a delta ion. Here it is in the form of a delta ion, and ion plus 6.63 or 6.67 percentage, which is called as a cementite. So these are all the different structures you have to notice that. So here it is pearlite plus ferrite, and at the 0.8 percentage it is pure form of the pearlite, and beyond that pearlite plus cementite. And here the cast iron form, you can notice that cementite plus pearlite is transformed to leduborite. It is transformed to leduborite. Pearlite and cementite will form into leduborite. And here we can notice that this is austenitic plus cementite plus cement leduborite structure. This is cementite and leduborite structure, and this is the gamma ion. Here if you can notice that in this point it is in the austenitic point, 1.7 percentage of carbon, that is austenitic steel, that you have to notice. And beyond this line, beyond this line, these are all in the form of a liquid state at the form of the line, and this line, it is in the form of liquidous state, and here it is in the form of pure solid state. So this you have to notice that. And at 723 degrees Celsius, at the 723 degrees Celsius, the steel, whatever may be the steel, which loses the magnetic property, and that is called as a iron Curie point. So this line is called as a Curie line. You have to notice that this line is called as a Curie line. And we have to do a lot more with the theories. Okay, with this small information, I'm going to carry the theory content for your information. Yes, the iron carbon equilibrium diagram is the iron plus carbon, that is iron carbon family diagram. The melting point of an iron is 1536 degrees Celsius, and this iron carbon diagram is an binary phase diagram which involves two components. One is iron and another one is the carbon percentage. The percentage of carbon in x axis and the temperature in the y axis. And left hand side, some of the diagrams we can see the structures. And here the structures, only two types of structures are involved in iron carbon diagram, that is BCC and FCC structure, body center cubic and face center cubic. Your alpha and delta ferrite is in the form of BCC ion, and your gamma is in the form of FCC ion. Gamma is in the form of FCC structure. Here we have four types of ions: alpha, beta, gamma, and delta, where beta is an unstable one, and alpha, gamma, and delta all are ferritic and austenitic and delta ferrite ions. Here you can notice that the figure gives the percentage of carbon and the forms. Iron plus 0.25 percentage of carbon, it is the ferrite form. Iron plus 1.17 percentage of carbon gives an austenitic structure. Iron plus 4.3 percentage of carbon, it is give a lead form. And iron plus 0.8 percentage of carbon will give perlite. We know that the composition of the perlite is the cementite plus ferrite. The perlite of the 100% means the ferrite of 87 percentage and cementite of 13 percentage. That is perlite in the form of Fe3C plus alpha Fe. Fe means iron, C means carbon. So that is our understanding. And the 1.1 percentage of carbon plus iron will form a delta ion, and a carbon iron plus 6.63 percentage of carbon will give cementite structure. The maximum solubility of the carbon in the iron is 6.67 percentage or 6.63 percentage. And here we have to notice that isomorphous is the soluble in both solid and liquid state. This we have to notice that. And here the eutectoid mixture of alpha ion, alpha Fe3C, is called perlite. The BCC structure of FeC solid solution is the ferrite, and FCC form of FeC solid solution is called as an austenite. So this is the definition of perlite, ferrite, and austenite. So the definition of the perlite, once again I am repeating, the perlite is the eutectoid mixture of alpha plus Fe3C, and ferrite is the BCC structure of FeC solid solution, and austenite is the FCC structure of FeC solid solution. This we have to notice that. And here I have given a detailed picture. This is a beautiful hint. You can please notice this. The steel we can divide it in form of three types. One is Eutectoid. It is having 0.8 percentage of carbon, and hypoeutectoid. It is in the form of 0.0252 0.8 percentage of carbon, that is perlite plus alpha ferrite, that is in the form of BCC structure, and here it is gamma austenite. Gamma austenite is in the form of FCC structure. Please notice this, gamma austenite is in the form of FCC structure, and hypereutectoid 0.81 to 2.1 percentage of carbon. Here the phases are perlite and cementite, both are in BCC structure, whereas in the above austenitic solution, the gamma austenitic becomes FCC structure. Here I'm going to give this thing in the diagram. Here, up to this, it is in the form of BCC structure. Beyond this, if it goes to the latebrate, sorry, excuse me. So this is in the form of BCC structure, and this one in the form of FCC structure. So this we have to notice this. This is in the alpha phase. This is in the gamma phase. This is in the alpha phase. Okay, so this is the thing that illustrated. Similarly, for the cast iron is also subdivided into three components. One is eutectic and hypoeutectic and hypereutectic. Where eutectic is the 4.3 percentage of carbon, and hypoeutectic is the 2.1 to 4.3 percentage of carbon. This is in the perlite. If it is in the perlite form, it follows BCC structure. If the austenite plus ledeborite is in the form of FCC structure, in the hypereutectic cast iron, 4.3 to 6.67 percentage of carbon, it is in the perlite, in the pure perlite in the BCC structure, and in the FCC structure it is in the form of cementite and ledeborite. Whenever you can see the cementite is having a maximum percentage of carbon. This you have to notice that. And cementite is the hardest form of the material. When the carbon percentage is more, your iron becomes harder and harder and harder. So this is a point you have to remember. And next, we're going to remember some of the points. This alpha ion is a solid state. Alpha ion is in the solid state. The ferrite is stable up to 910 degrees Celsius. The ferrite is stable up to 910 degrees Celsius. Beyond 910 degrees Celsius, there is no ferrite state, alpha ferrite. There is a gamma austenite will come into picture. And iron carbon and crystal lattice. In iron carbide crystal lattice in the form of cementite structure, and phase change on heat and cold. So this is the Fe3C diagram. The iron carbon diagram is the phase change diagram, which will represents both hot and cold condition. When we can heat, it follows this thing, this figure, and when we cool, this is forms the another figure, the same figure, sorry. And Fe3C diagram represents correlation between microstructure and properties. Yes, with the iron carbon diagram, we can take the enough microstructures of the iron and carbon phases. So here you have to notice that in the eutectoid, the maximum temperature is 723 degrees Celsius. At that juncture, it will in the form of ferrite plus cementite. Ferrite plus cementite is in the form of the perlite. It will pertaining state of equilibrium between three state of phases. Three state of phases, it will get an equilibrium condition. And eutectic in the form of the temperature of 1147 degrees Celsius, it is in the phases of austenite plus cementite. It does not exhibit mushy zone out there. And next one is the perieutectic. Perieutectic is present at the topmost level of the delta of ferrite, which will have 0.1 percentage of carbon and its temperature is 1450 degrees Celsius. So it is in the form of perieutectic is in the form of a liquid state, 100% liquid state, and the perlite is present in up to 725 degrees Celsius. Here, the perlite is the alternate layer of ferrite and cementite, where ferrite of 87 percentage and cementite of 13 percentage is available at the perlite. Next, the leduburite at 1150 degrees Celsius at the eutectic temperature at the 4.3 percentage of carbon, the leduburite is in the form of austenite plus cementite. And austenite, you can't exist, it can't exist above 723 degrees Celsius. You cannot see at room temperature also. So between the room temperature to 723 degrees Celsius, it exists. Next is the Curie point. Curie point, which is the magnetic property is converted into non-magnetic property, that is called as a Curie point. The Curie temperature is 768 degrees Celsius. The cooling curve of time temperature transformation diagram of 1600 degrees Celsius and melting temperature of the phase change of 1536 or 39 degrees Celsius. The Curie point is present in delta ion of BCC structure in 1400 and 400 degrees Celsius. It will present in alpha ferrite, that is austenitic FCC non-magnetic structure at 910 degrees Celsius, and alpha ferrite at ferrite and BCC non-magnetic structure at 768 degrees Celsius, and alpha ferrite in the perlite form of BCC magnetic and below 763 to room temperature it will be in the magnetic form. Next, we are going to give some of the glimpse in the crystal structures. The eutectoid and perlitic, all three structures we are going to discuss here. Eutectoid, the single solid solution is converted into two solid solution. Here, the excellent combination of strength and ductility we will get at the face of perlite and the structure of lamellar structure, the face of perlite. And eudectic is the in the form of the input of liquid phase is converted into two solid phases. The phases are leduburites and the structure is the lamellar structure. Here, perieutectic. Perieutectic is the in the input the liquidous state, that is the solid plus liquid, which will be converted into a solid. The phase is austenitic phase and the structure is FCC structure. Here I am going to give some of the glimpse. The plain carbon steels, the mild steel having a carbon percentage of 0.3 percentage of carbon, and high carbon steel it is in the form of 0.6 to 1.7 percentage of carbon, and the medium carbon steel is 0.5 to 0.3 to 0.6 percentage of carbon is called as a medium carbon steel, and mild steel we know that it is a low carbon steel. And in the higher in the cast iron it is having 2 to 4.5 percentage of carbon, and cementite it is having 6.6 percentage of carbon. It is very hard and brittle. And ferrite is in the form of 0 to 0.025 percentage of carbon, and it is more in soft and ductile. Next, we are going to see the phase change diagram. In the phase change diagram, we have noticed that we have a four phases. It starts from spheroidite and coarse perlite, fine perlite, and to martensite. Here, the coarse perlite is softer than fine perlite. This we have to notice that coarse perlite. The coarse structure is always softer than the fine structure. Here, the very soft material is the spheroid. Very soft structure is the spheroid structure, and very hard structure is the martensitic structure. So spheroid is first, and coarse perlite is little bit harder than spheroid, and fine perlite is little bit harder than coarse perlite, and the martensite is little bit harder than fine perlite. So this we have to orderize. And next, the reactions, the different types of phase reactions and the input and output are given here. Here first one is the eutectic. Eutectic reaction, the input is in the form of a liquid state, that is its temperature is 1147 degrees Celsius. It is in the form of lead structure, and it contains 4.3 percentage of carbon of liquid is converted into two different solids, that is austenite plus cementite. The solids are in the form of austenite and cementite. This is one solid and this is one solid. The liquid, lead liquid is converted into austenite plus cementite. That is our understanding. Next is the eutectoid. The eutectoid, it is in the input is in the form of the solid state, where it contains 0.6 percentage of carbon and 723 degrees Celsius. It is in the form of perlite. It is converted into two different solids, that is austenite to perlite. We know that the perlite is having ferrite and cementite. So ferrite is one type of a solid, cementite is one type of a solid. So that is our understanding. Here the perieutectic, we give the liquid metals in the input, that is liquid plus solid at 1492 degrees Celsius, that is in the form of delta ion, and it contains 0.18 percentage of carbon. It is presented in A3 line. So when the output, when it is solidifies, the output will becomes a single solid. It will becomes a single solid, that is delta ion. And perieutectoid, we give two solids and it will produce one solid. And monoeutectic, the liquid phase is converted into liquid plus solid phase. The monoeutectic, the liquid phase is converted into liquid plus solid phase. So this is available at the A4 line, that is at the cast iron, the topmost cast iron line. It is in the form of liquidous line, that is liquid plus solid. The monoeutectoid, the solid is converted into two different solids, two different solids. So this you have to understand. And here uh, I'm going to give some of the ferrite and austenitic stabilizers. Ferrite stabilizers like chromium, tungsten, molybdenum, vanadium and silicon are the ferrite stabilizers, and austenitic stabilizers are magnesium, nickel, copper and cobalt, all the austenitic stabilizer. So here we have to notice that A1 line, the above critical recrystallization temperature or critical temperature, that is 768 degrees Celsius, austenite transformation to perlite and ferrite. And ACM is the curved line. ACM is the curved line which connects A1 and A3. The limit of carbon solubility in the form of austenite. A2 is the imaginary line. A2 is the imaginary line between 800 degrees Celsius to 900 degrees Celsius. And A3 is the beginning of transition from austenitic to ferrite, that is perieutectoid, perieutectic steel. I hope with this I have given enough idea about the iron carbon equilibrium diagram. With this, I would like to thank you all for the patient listening. Thank you.